All right, welcome back to day 16 of Advent of Code 2022. Since last time, I realized that some of the other videos I've made, it's like I have an audio filter set up in my recording software because I have some static from my microphone, or not static, just some kind of background noise that I wanted to get rid of. And apparently that noise filter removed a lot of the F's and C's and like starts of a lot of words. So my reading the the problems aloud has sounded weird. I didn't realize until I played it back a couple of days ago. So I changed that. I hope that the noise we get instead isn't too bad. Yeah. Otherwise, I think let's just get right into it and let's see how it goes. Okay. So day 16. Proboscidae volcanium. The sensors have led you to the origin of the distress signal, yet another handheld device just like the one the elves gave you. However, you don't see any elves around. Instead, the device is surrounded by elephants. They must have gotten lost in the tunnels, and one of the elephants apparently figured out how to turn on the distress signal. The ground rumbles again, much stronger this time. What kind of cave is this exactly? You scan the cave with your handheld device. It reports mostly igneous rock, some ash, pockets of pressurized gas, magma. This isn't just a cave, it's a volcano. You need to get the elephants out of here quickly. Your device estimates that you have 30 minutes before the volcano erupts, so you don't have time to go back out the way you came in. You scan the cave for other options and discover a network of pipes and pressure release valves. You aren't sure how such a system got into a volcano, but you don't have time to complain. Your device produces a report, which is your puzzle input, of each valve's flow rate if it were opened in pressure per minute. It's not pressure per minute, it's flow. Anyway, and the tunnels you could use to move between the valves. There's even a valve in the room you and the elephants are currently standing in, labeled AA. You estimate it will take you 1 minute to open a single valve and 1 minute to follow any tunnel from one valve to another. What is the most pressure you could release? For example, suppose you had the following scan output. Okay, so we have valves AA through JJ. Note, some of them have rate 0, not only AA, but several of them do. And then we see what we have the rate for each of them, and we can see which other valves we can go to. Obviously, these ones aren't really valves; they're just waypoints in a graph. Okay, all of the valves begin closed. You start at valve AA, but it must be damaged or jammed or something. Its flow rate is 0, so there's no point in opening it. However, you could spend 1 minute moving to valve BB and another minute opening it. Doing so would release pressure during the remaining 28 minutes at a flow rate of 13, a total eventual pressure release of 28 times 13 equals 364. Then you could spend your 3rd minute moving to valve CC and your 4th minute opening it, providing an additional 26 minutes of eventual pressure release at a flow rate of 2, or 52 total pressure release by valve CC. Making your way through the tunnels like this, you could probably open many or all of the valves by the time 30 minutes have elapsed. However, you need to release as much pressure as possible, so you'll need to be methodical. Instead, consider this approach. Okay, so minute 1, no valves are open. You move to valve D, and then you open valve D. D is going, releasing 20 pressure. You move to valve C. You move to valve B. You open valve B. You move to valve A. Blah, 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 etc., etc. And ultimately, it all adds up to 1651. So work out the steps to release the most pressure in 30 minutes. And what is the most pressure you can release? Now, I actually ended up just letting go of this one. So I sat there. If anyone watched the live stream, no one did. But, if you were to rewatch it, a lot of staring at it, a lot of barking up wrong trees and stuff. So yeah, I ended up going to bed, and looking for a hint to kind of get through it. And I can see that one of the things that I wanted to do when I was doing this, when I was trying to do it last night, was I wanted to find out how much it would cost to go from each node to another, or from each valve to another. But it seemed too computationally intensive. It didn't seem like the right way to go. As I mentioned yesterday, usually when you find the right solution to these problems, the result is there like that. And anything I could think of would just take forever. So I was looking at different graph searching algorithms that I could think of, but they just, nothing really fit the bill. It was all really awkward. I tried for a long time, probably because I saw we had to use, was that yesterday? I think yesterday we had to use Dijkstra, and last year, right after having to use Dijkstra, we had to use another graph search algorithm called A star, and I don't know, I just got that into my head, thought that's what I had to do, and that got me nowhere. So it was funny. So I didn't know I didn't know how to approach this. I tried a lot of different things and didn't really get anywhere. And then after a couple of hours, and I decided to call it a day, I went to YouTube and just to see how have other people solved this. That's not true. I went to the leaderboard first, and usually if you look at the leaderboard, the top the top 100 are usually done. Sometimes if they're really easy, they're done within 5 minutes. But I don't think I've ever seen it be more than like maybe 10, 15 minutes or so. Last night it was, I think number 100 was over an hour. And so, that made me feel a little better that, that, they were using, orders of magnitude more time on this almost, as was I. So that was reassuring. But yeah, I had a feeling that there was something I wasn't getting, and since I want to do these every day, I cheated a little bit. I guess I went and looked for a hint. But yeah, as I was saying, couldn't find anything, couldn't find it out, and then I looked at the leaderboard, and then I went to YouTube. Usually you can just type in Advent of Code 2022 day whatever, and there's going to be a bunch of solutions. Last night there wasn't any. And then I kept scrolling, and then I ended up found one guy who had done it, and it was in a programming language I had never even heard of, and he was using an algorithm that I didn't know, and trying to work out what an algorithm does in a language that you don't know, especially when it's very thoroughly optimized. Oh, by the way, I will leave a link somewhere. Let's see, like here maybe. Let's try to his video where you can see how he does it. I looked up that programming language today, and it turns out that it's a programming language that this dude made, and he's probably the only one using it. So no wonder I'd never heard of it. But so the thing that he used was an algorithm called Floyd-Warshall that I had never heard of, and seeing what that does, I'm like, yeah. If I had that in my toolbox, this would have been a much more approachable problem. So, all right, so let's take a look at what this looks like. Okay. All right, so let's look at some code. All right. I should get into the habit of ordering this by how I want to talk about it. Not today, obviously. All right, part A. This is, as usual, we get all the lines from the file, and then we parse them. Parsing it was not too bad this time. That's a lie. There was a lot of, I took an example from the sample file right here. Copy. Yep. Yeah, just took an example, threw it in here to compile a regular expression. It replaced, the things that I want to find with, parenthesized patterns, and I thought I would be good to go. Evidently not, because see, tunnel and tunnel, and leads and lead, and valves and valve, and it took me a while to realize that. So I had somewhere that just didn't get parsed. They just skipped over, and I'm like, what? That's weird. So I had to add all these question marks because these S's may or may not be there. So that's how regular expressions work. So you specify the whole thing, and then anything that's in a parenthesis anything in parentheses turns into a group, which we'll use down here. So valve, so that's the name of the valve. We get yep, that's what they look like. Okay, so valve, I have double A, and flow rate, that's a number back, yeah, okay. \W is any character that is that might be part of a word, so letters, right? And plus means that there is going to be one or more. Hasflow is going to be the same, rate equals \D is digits, and there is one or more of those, and then tunnel, and the S is optional, leads, S is optional, valves, S is optional, and then, yeah, just whatever the rest is. So I use that down here, go through the lines. Yeah, none of these anymore. That was from when I was debugging it. Okay. I should do that still. Okay. So after running this, groups now is an array with 1, 2, 3 elements, name, rate, and tunnels. And then I create this V. I haven't really decided if that's short for valves or vertices. Let's just call it valves. I like to call vertices nodes instead. Yeah, so we have name, rate, and tunnels, and we use the name as the key in this dictionary. We turn the rate into an integer, and we split based comma space. So that means tunnels here. No, this second part of this tuple is going to be a list with 3 elements, DD, II, and BB. That's pretty straightforward. So that's what we get out of parse lines. So that's what we get up here. Why is that underlined? It's not defined. Did I mess something up? We'll see. No, actually, I do really want to do that. Oh, okay. And then I can get rid. Yeah, sorry about that. That should do the trick. Yep, okay. Okay, so we parse the lines and we get a dictionary back that has keys that are names of the valves, and the values are a 2-tuple that has the flow rate and the neighboring tunnels, or whatever tunnels that you can reach from this specific valve. So once we have that, it's really a relatively... Oh, no, right. here comes the Floyd-Warshall thing. Now, this is real cool. So what Floyd-Warshall does is it, in a very reasonable amount of time, it calculates the time to go from any node to any other node. So once it's done running, you have a dictionary that basically, like if you go, if I want to go from AA to BB, you know this is going to be, however many steps that's going to take. And it's directed, this isn't necessarily the same, with B. It's not the same. It just works through the whole thing, and it's pretty clever. Let's take a look at that now. Yeah, sure. Okay. Okay, so here is how Floyd-Warshall works. Okay, so we start by initializing this matrix. It's multi-dimensional associative array, or multi-dimensional dictionaries. So we start by creating an empty array called dist, or distances, and then we go through all the different keys, and for where keys are valves. So we go through all the different valves that are in our valve dictionary. And then we create like a sub-dictionary for that particular key. And then we go through all the keys once more. And if they are the same, so if K is AA and K2 is AA, then we set it to 0, because obviously going to where you are is free. And if it's not the same, then we set it to infinity. All right, so far we have as far as we know, you can't go from K to K2, so we set it to infinity. Next up, we go through all the keys once more, and let's see here. So V of K gives us the tuple corresponding to that valve, and the one index is the tunnels, the list of tunnels. So K here is going to be some valve, and T is going to be one of the valves that it says that it can, like if we're looking at valve AA, then T is going to be first DD, then II, and then BB. Okay. And since they are neighbors, and nothing special about the weights here, so we just set that to 1. So far, like, no surprises, right? Like anything that's this is all like pretty straightforward stuff. There's you just create the whole array, or the whole like matrix. You set, going to yourself is free, going anywhere else is infinity. And then you say anything that we know, because it's given in our input, is going to be a neighbor, is one step away. And now comes the fun part. Okay, so for K so we have 3 nested loops here, K, I, and J, that all go through all the different keys. And then it checks if the distance from Y to K plus the distance from K to J, if that's less than the distance from I to J, then we set the distance from I to J to be distance from IK to distance from K to J. And once we're done with all of that, we've resolved every single we've considered every path, and the output ends up being, just like all the distances, because everything. The point is, the recursive step is looks at, okay, so for everything that I've looked at so far, going from here to here, let's just, you know, in the first case, you think it's infinity, right? But then if there's if going from, if I want to go from here to here, and, you know, so far, you know, as far as I know, the cost to do that is infinity. Well, what if I know that going from here to over here, and I know that going from here to over here is not infinity. Well, that means that going from the distance from here to here is going to be, you know, this plus that. Does that make sense? Hope so. Otherwise, if something that's clear, let me know in the comments, and I'll try to make a better video explaining this. But what we need to know right now is that the output of this algorithm is a two-dimensional matrix that tells us exactly how, like, the cost of going from any one node to any other node anywhere in the graph. Super cool. Okay, part A. So that gives us all the distances, and then we have a depth first search, where we put in the valves, the distances, the starting point, and start time is, yeah, how much time is left, which is 30 to begin with. And this right here, so the thing to realize is, excuse me, so we have this whole map. Yeah, we we have the whole map. There's a bunch of valves. They aren't, we don't need to consider them valves because we're never going to open them. And the goal is to get as much, to release as much pressure as possible over time. So obviously we're not just gonna hang around. We're not gonna go somewhere and just wait. So don't have to worry about like waiting or staying in a different in any place. So all we really need to look at is what is the order in which we want to open the valves. And you know, there's only so many ways to do that, and that's what we're doing here. So we filter out all the ones that are pointing at stuff. That's what we do here. So we go through all the keys, and we have this little lambda expression that we pass into filter, which takes v. So what filter does is it iterates through everything, like the second argument and onwards. And each of them gets, the function that is your first argument gets run on each element from here. And based on whether or not the result of that evaluation is truthy, it gets included in the output from filter. So what we do here is we look up v in the dictionary of valves, and if its flow rate is 0, then we don't really care, you know, the order in which we go there, right? It doesn't matter. It's just we know how much it's going to cost to go everywhere, so really we don't need to consider all the intermediary steps here. It doesn't matter. It's not going to change anything about, you know, the efficiency of of the draining, like opening all the valves. It's going to be the same thing. Okay, so let's look at the depth first search. Yeah. So ignore this up here for now. Let's just zoom in a little bit. Is that like that? Yeah, cool. Okay. So we have our depth first search here. So we pass in the valves, the distances. Cur is our current position. Rest is, you know, whatever's left, whatever we haven't visited yet. And then finally the time remaining. And if we're out of time, we're done. We're not going to get anything more out, so we return 0. Okay, then we set the base return value to 0, and then we go through Yeah, we go through this. Okay, so we have, let's look at choose one. It's up here. So I put a comment in here because I kind of struggled to explain it. I'm not sure this helps. So basically, you pass in a list, and what you get from choose one is one at a time. It grabs one value from the list, in order, but it doesn't really matter. It goes through all the values and returns that along with a list that has all the remaining elements in it. So if you pass in 1, 2, 3, excuse me, if you pass in 1, 2, 3, what you will get out is first time you're going to get 1 and a list that has 2 and 3 in it. Next you're going to get 2 and then a list that has 1 and 3 in it. And finally you're going to get 3 and a list that has 1 and 2 in it. So that's exactly what we need here. Because we choose one and then we need to know whatever is left. So we choose one, that's going to be our next place to go, and then the new rest that we need to look at. That's not relevant anymore. Okay, so we have the distances, all calculated ahead of time, so this is pretty easy. If the distance from where we are to where we are going, if that's less than the time we have left, then it's valid and we're going to go. Then we calculate the contribution that this is going to give us. So V next 0 is the flow rate of the valve that we're going to. And we multiply that by how much time is left right now, minus the time it takes to get there, and then minus 1 because it takes a minute to open the valve. So that's how much this is going to contribute to, opening this valve is going to contribute to the total. And then we recursively call DFS again, where we, instead of our current, as the current position, we pass in the next one, and as the rest, or remaining, valves that need to be visited, we pass we get those from new rest, because that's what choose one gave us. And then we subtract the time that was spent on this step. And yep, so we do all of that. So we find the best result recursively. Then we can compare that to our contribution plus that, compare that to what we have, what we currently know to be the maximum. And if it's greater, then we save it. And if it's not greater, then we just move on. And by the end of it, we return the maximum that we could get out, because that's what happens recursively here. And and that's it. That gives us the answer in Python prod. Did I do a bad thing? Oh, this is in part B. Okay. What's it? Oh, I didn't save it? There we go. Yep, that's pretty fast. So we got the 1651 and we got the 1701. That's it. That was part 1. Okie doke. Part 2. You're worried that even with an optimal approach, the pressure released won't be enough. What if you got one of the elephants to help you? Sure. It would take you 4 minutes to teach an elephant how to open the right valves in the right order, leaving you with only 26 minutes to actually execute your plan. Would having two of you working together be better, even if it means having less time? Assume that you teach the elephant before opening any valves yourself, giving you both the same full 26 minutes. In the example above, you could teach the elephant to help you as follows, and then it goes through like this whole situation here. With the elephant helping after 26 minutes, the best you could do would release at a total of 1707 pressure. With you and an elephant working together for 26 minutes, what is the most pressure you could release? Okay. Let's see here how we did that. So, part B. There we go. So these 3 lines, the exact same thing as before. Get the lines, parse the lines, and work out the distances. This is like literally the exact same thing. Now we have a different depth-first search called DFS2. We pass in, I think this is all the same stuff, except it's 26 seconds, minutes instead of 30. Let's see, DFS2. Yeah, ignore that again for a sec. Okay. Okay. So this here, I don't think we ever hit this, but just for good measure. If we are out of time, and there's anything left, we run DFS, so the same algorithm as before, with whatever is left, and then 26 seconds. So the thinking here is, we've gone through and we've worked out, what we're doing ourselves, and we ran out of time, and then we're looking at, okay, so whatever is left when we ran out of time, let's see how well the elephant can do the same thing. So basically what we're doing here is we're just saying, hey, elephant, if you have the rest, what is the best you could do? And then that's one answer. If rest is empty, then there's nothing left to do, and we just return 0. Okay, and again, we have the base case. So this is what would happen if we just let the elephant do the whole thing, which would be the exact same as if we did it ourselves. So that would be like the 1701, right? No, not 1701, because we only have 26 seconds. Anyway, this is what you would get if the elephant did the whole thing. And then we do almost the same thing again. We have this loop. Again, we choose one, so we have whatever gets passed in. We take one element and the rest of them. And if we can get there in time, if we have enough time to move there, then we calculate our contribution just like we did before. We find out what is the flow rate of the valve that we've determined is going to be our destination, multiply by how much time is left, minus how long time it would take to get there, minus the time it takes to open the valve. That's our contribution. Yep. Then we try calling ourselves again. So we call DFS2 with, again, same V, same distances, next, so that the current position of us is going to be whatever we chose up here, and whatever is left then, and then subtract all the time remaining. And we add that, so that finds the best the best we can do, with this smaller problem, and eventually that comes down to a problem that is trivial here, and then the recursion stops. We add contribution, and if that's more than our base case, which was just let the elephant do the whole thing, if we can do it better by what we are doing, plus recursively how long time the rest would take, if that's greater, we store that as RV and we keep going, and eventually we return and the recursion stops and we're done. I don't know how long this actually takes as is. I didn't benchmark that. But I ran this and it took a lot longer than I felt like it should. And then I added, so instead of I renamed my DFS2 to DFS2 underscore, and then I created this caching wrapper. Which takes the exact same arguments, and then it creates a key based on current position, what is left, and how much time is left. Because that's the only thing that matters when we call this function, right? So if we're being called again with the same arguments, v and distances, they never change, right? After we parse them out, so they don't have to be part of the key. But we have cur and rest and time remaining. We have to turn rest as a list, which is not hashable. If it's not hashable, you can't use it as a key in a dictionary. So I just turn it into a tuple. And if we don't already, and we have the cache dictionary up here, if we haven't already seen that, then we go ahead and call the function and store the result and then return the result. That's it. And I have the same exact thing up here for DFS. And with that optimization, it all happened, I think it takes 14 seconds-ish. We can let it run. And then we can try without the optimization after. Let's see. Is that all of it? Or is there anything in here that we haven't talked about? Nope, I think that's just about it. Yeah, 14.7 seconds. And that's with this, pretty aggressive optimization. Yeah, but, I got there. I don't know if there's a faster way to do this. This feels pretty clean. I don't know, maybe. Maybe. Yeah, so actually, I want to share this in case you don't know. So if we had a DFS3 that so there's something called functools, which is a library of cool stuff in Python. I think it's part of the standard library. Yeah, I think so. One of the things you have in functools is a caching wrapper, just like the one I have here. And if you were to use that, you can use, yep, Copilot knows what's going on. Could just be cache, doesn't have to be LRU. We don't care about that. This would do it. In a lot of situations, this is all you need to do. But because we're passing in v and distances, both dictionaries can't be hashed, so you can't use them as keys. Also, rest is a list, also not hashable, but you can easily turn it into a tuple, and then you're fine, right? Because they're just integers. There's nothing particularly interesting going on. But yeah, if these had been hashable, this is all I would have needed to do. Just do functools, the cache, and done. But no such luck, not this time. Yeah, we can talk about the LRU cache some other time. But otherwise, I think that was I think that's it for today. No, I don't want to. I wonder how long time it takes without these optimizations, now that I know they're right. Yeah, sure. Let's try. I can always, you don't have to hang, no. You don't have to hang around for it. I can cut that bit out. You just wait until we get the answer. That's it, right? This is probably going to be a while. I mean, that's a lot of operations that you're saving by doing that caching. Yeah. So let's see. I'll just do something else in the meantime. Yeah. Yeah, this takes a while. I'm just gonna pause now. Let's see. Okay, I think I'm just gonna I'm just gonna let this run. I don't want to wait for. That's my laundry done. Yeah, I don't want to wait for this to finish before I can publish the video. So I will try to remember to tell you tomorrow how long it took. But for now, that's it for day 16. I hope you enjoy this. If you have any questions or comments, leave them below. Like and subscribe, and I will see you tomorrow.